Hey, it's Plumber Tom. Don't forget to check in the comments below for a link where you can find additional resources like practice tests and courses that you can take. Your support helps me to be able to create more great content. Thanks for watching. Hello and welcome to this video presentation of the International Mechanical Code as we continue our study of Chapter 10. My name is Thomas, and in this video presentation we are going to proceed from section 1007 to 1011, or basically let's just try to finish off this chapter. Grab your books, be ready to mark as we go. Let's get into it. In the last video presentation, you might recall that we talked a lot about different safety devices, and we will continue some of that here as we finish off this chapter. Starting with 1007, we look at boiler low water cutoff. Let's go back to the fundamentals here. When you have a boiler, it does over time lose water. That can happen. If that water gets too low, then we get into dangerous situations, right? Because if there's no water in there and it's heating like crazy, then we overheat and it can possibly explode. We don't want that to happen. So one of the safeties, of course, is the low water cutoff. There are a variety of devices for boiler low water cutoff. This one would connect directly to the side of a steam boiler. It's connected to the water chamber of that boiler, and as that water level goes down, it's directly affecting this low water cutoff. If it's too low, it will shut off the boiler. But there are other devices that simply probe the boiler chamber. They'll thread directly into that, and if the water's too low there, then it will, of course, shut off the electrical. Here's another example of something like that. It threads into the side, and it has an electrical connection that can stop that circuit. Let's have a look at this diagram. This comes out of the code commentary. Listen to the title for this diagram. Simplified sample wiring schematic for basic gas-fired boiler. Now, as a plumber, I look at all these lines on a page. It doesn't look too simple to me. But don't worry, it's not as bad as it looks. And we can learn a lot from this about the importance of these safety devices and the way that they interrupt the power. So let's have a quick look over this diagram. Okay, follow me here. We were told in our last presentation that a boiler should only have 2 wires in its electrical connection. We see that here. The bottom is L1, that's the hot wire, that's what's feeding electricity into here, and then you've got L2 on the top, and that's the neutral. So across the bottom, we see a whole bunch of interrupts, right? Follow me. We've got the disconnect switch, that's what I can turn off. There's a fuse that can burn out and shut it off. There's a float type low water cutoff. We've talked about that. So if there's not enough water, it kills the electricity. There's a pressure limit control. Too much pressure kills the electricity. There's a temperature limit control. Too hot kills the electricity. A series of 5 different things that can shut off the power if there's a problem. Now, this line continues up and goes through a transformer. This takes the high voltage, that's 120, down to a 24. So on the right side of this, we're seeing the control wiring at a lower voltage. We have another series of optional safety controls with a low water cutoff, a pressure limiting switch, a temperature limiting switch on the control side. Now again, I'm no electrician, but it's pretty obvious that there are a lot of safeties involved here that can kill the power if there's a problem. Yes, control. Section 1008 is about bottom blow-off valves. And those are pretty much what they sound like. You have the bottom of the boiler, and there's an outlet with a valve that will blow off. Now, what do you expect you would find in the bottom of a boiler? Well, what do you find in the bottom of a water heater? A tank-type water heater, you will often find sediment. Sediment building up, yes. That could be a problem if it builds up in the bottom of the boiler. And so, there's a valve to release that. The requirements for these blow-off valves is that they have to be installed in the opening on the boiler. That means there's a threaded inlet or somewhere they can connect directly to that boiler tank. And if the maximum working pressure is over 100 psi, then it has to have 2 of these blow-off valves. Now, the basic function of these is to open quickly and let out a burst of pressure. Think about how would you try and move sediment out of the bottom? You'd want to just kind of open and close and let it pop out, right? Now, if we just let it open and flow out, then we have another problem because we let a whole bunch of water out of a steam boiler. And we were just looking at 1007, where we talk about low water cutoff. We could kill this thing if we let too much water out at once. So these valves are designed to release a little amount in a big, quick burst. Just poof, poof, poof. And you can do that manually. There's levers you could open and close those. But that allows for that movement of sediment out of the steam boiler. Now, of course, all the piping involved would need to keep that safe because the last thing you'd want to do is be blasting someone else or yourself with superheated sediment. That said, the discharge for a bottom blow-off valve needs to be discharged to a safe place. And of course, we're going to play by the rules of International Plumbing Code, do some indirect waste, air gap, and then we'll be in good shape. Oh, by the way, we probably also should consider the temperature of whatever's blowing out of there. Anything more than 140, according to plumbing code, shouldn't be going down the drain just yet. Let it cool. And I personally don't know how much sediment is coming out of there, but you also probably wouldn't want to put too much of that down the drain, so you might have to be careful about what's coming on the back end of that blow-off valve. Let's talk about a topic that's far more familiar to all of us, and that is in 1009, hot water boiler expansion tanks. Well, maybe you don't know much about the boiler variety, but you know about expansion tanks by now. And we install them all the time on hot water systems. 1009.1 talks about where these expansion tanks are required, and pretty much an expansion tank should be installed to every hot water system. And we see that on the potable, on our domestic hot water, but especially on these heating systems, we're going to need these. Now, there are a variety of options when it comes to expansion tanks. This is the most common. This is what we use all the time on the potable side. It's a closed type expansion tank with a diaphragm. You have a water chamber and an air chamber. The air chamber will compress as the hot water expands. And you can get these in a lot of different sizes. We always install like the 2 gallon or the 5 gallon or whatever, those little ones. There are some huge ones out there.
ほら、僕は大きなタンクだ。よろしくお願いします。
And a large hot water heating system is going to need a big expansion tank, right? But there are other possibilities for expansion. Now, this is still a closed type. That means the whole system is sealed up. We don't have anything like open. But on this type, there is a chamber with air in it, and that water is able to push in and out of there as it expands. A sight glass on the side would help you to see how that's functioning and whether the water's in there or what level it's at. But this type of expansion tank are less common because that air can be compromised inside of there, meaning it can dissipate into the water. You can fill the whole thing up with water, and then you'd have to drain it down and get air back in there. So it's an expansion tank that works in the same way as you compress the air or allow water to push into the chamber, but you constantly have to be maintaining that chamber. And because it's higher maintenance, most of the time we don't use these anymore. We go to the diaphragm type because we don't have to work for that afterwards, right? There's a separation between the water and the air, and we don't have to refill the air all the time. Does that make sense? There are some really fancy calculus-looking equations for how to calculate the size of your expansion tank right here in Chapter 10. I invite you to stare at those for as long as you want and see if you can make any sense out of it. But there is also a table, 1009.2, and this gives us the volume of the system on the left column. So depending on, we're talking all the pipes, everything involved with the whole system. Depending on the size of that, you're going to be sizing out your expansion tank, right? So we have the different types of tanks that we just looked at. The pressurized diaphragm, that's the one with a separate air chamber that we use most of the time, and it gives the size of that tank in gallons in relation to the size of the system in gallons. So for example, if I have a 200-gallon system, I'd need a 17-gallon expansion tank. Similarly, we have the non-pressurized type. That's that other chamber we were looking at. And you see the numbers are a little different. It needs a larger reservoir because it's less reliable, or that air chamber can be compromised. And so we see a difference on the size of that type of tank. Now, again, these are much larger systems than we are normally installing on potable water, but obviously those expansion tanks need to be big enough to allow for the expansion of a big system.
さあ、これから僕はお前の小さなタンクを食べよう。
Now, there is one other type that's mentioned in 1009.3, and this is the open type expansion tank. The other two were closed or sealed in with the system. This one actually has an opening to the atmosphere, meaning water can push in and go out of this tank. Similarly, it has a sight glass on the side where you can see the water level and what's happening inside the tank, but the air is not compressing as much as it's just pushing out into open air, or being drawn back in. As the water goes down, air can flow back in. This is a really old method for handling thermal expansion, so we don't see many of these anymore, but they are addressed here in 1009.3. In order for an open type expansion tank to work properly, it has to be elevated physically above everything else, above the heat source. It says open type expansion tanks shall be located not less than 4 feet above the highest heating element. So there is that positioning that we have to take into account for these as well.
Hey, why are pipes so bad at keeping secrets? Because they always burst under pressure.
Section 1010 is about gauges. Can you imagine trying to keep safe a boiler that's heating water when you have no idea what the pressure or temperature is? That is going to be difficult. It's really helpful to be able to look at a gauge and see what is happening on the inside. We can anticipate if there's a problem, if something's out of control. So 1010.1 states that every hot water boiler shall have a pressure gauge and a temperature gauge, or you can have a combination pressure and temperature gauge like we see here. You can look at the single face and get all the information at once. Either way, it's important to get both of those readings. On a steam boiler, there's a different type of gauge. It's a water gauge glass, a piece of glass tubing attached to the side of the boiler that can actually give you a visual on the water level within that system. A steam boiler should have a good reservoir of water that's being heated and a chamber of steam on top of that. And we can easily detect that if there's a tube on the outside set up with these valves. You can see how this all fits together. And it's going to tell me immediately, here's the water level. I'm in a good place. Or maybe I'm not. Steam boilers should also be equipped with a pressure gauge. As with anything else that we install, it is important for us to test our work. No amount of safety devices can correct issues that are caused by improper installation. So we have to test everything out first, and that's what 1011 is all about. It says that we have to test the whole system upon completion of installation. We should, of course, do that according to the manufacturer's requirements. They may have specific step-by-step testing that we would need to follow. All of these tests must be approved, meaning an inspector would come and verify that things are as they ought to be, and a copy of all the documents should be submitted to the code official. Why would you do that? Why would you give documents to the inspector? That inspector is supposed to make sure that you did it right. So they're going to need to look through and understand what's required and then verify that you did it right. That's the intended process. Now, when it comes to tests, any testing that we need to do, including on piping or other parts of the system, we're going to be using gauges. And this section, 1011.2, specifies what sort of gauges we should use. A gauge should not be less than 1 1.5 times the working pressure. What we're looking for there is the working pressure plus enough room to see if we are above that pressure above or below, right? However, we also don't want a gauge that's way out there, that has way too much of a range, so not greater than 4 times the maximum test pressure. We need to be able to see on the gauge if there are issues. And if the pressure on my gauge goes way higher than my test pressure, it's going to be hard to tell if there's any loss or variance or issues like that. So that's the range that we should be using as we test all of this out. So that does it for our study of the International Mechanical Code, Chapter 10. Really not a very long one, right? It doesn't take too long to read through those couple of pages. Hopefully our discussions here have helped you to understand more about what those different sections mean and the way that they apply to the installation of these boilers, water heaters, and pressure vessels. Thanks again for watching. I'll see you next time.